Oh, I'm going backwards.
Okay, we'll start the last session today. We have three talks, and then we'll go for a discussion. We're focused on the observations. So first talk is from John Braun. He's going to talk about more on COSMIC-2 data for the space weather.
Thanks, Sue. So this is people who know Cosmic will know much of this talk. But I kind of listening to the presentations this morning and the discussion, I'm going to try to mix in some things that I think might be relevant, not just for COSMIC-2, but for just general data systems that might be available in the future for satellite, for space weather data assimilation. So for people who don't know, I'll just give there's a couple of little background slides here. So COSMIC-2 is really a mission that has neutral atmospheric component, but the majority of the science details and how the orientation of COSMIC-2 was built was really focused on space weather and equatorial space weather. COSMIC-2 has three payloads. It has a primary payload and two science payloads. So it has the primary payload is a tri-GNSS radio occultation system, and it has a POD antenna, precise orbit discrimination antenna, on the fore and on the aft side of the spacecraft. And then it has a radio occultation antenna on the fore and the aft side of the spacecraft. So from an ionosphere point of view, all of the data from TGRS is going to be coming from the POD antenna. And that is really because, normally POD is a topside measurement. So it is basically spacecraft altitude up. But these antennas are pointed so that they can basically observe from zenith all the way down to below 90 kilometers tangent point altitude. And so that is an operational data product or an operational instrument. We deliver data products to the 557th Weather Wing and also to NOAA SWPC Space Weather Office. And then the secondary instrument is the ion velocity meter. The IVM provides operational in situ density measurements that are delivered to both 557th and SWPC. And then there is an RF beacon here on the bottom, which is broadcasting at 3 different frequencies and requires the use of an RFB receiver, some operated somewhere on the ground. I do not really talk about RF beacon antennas at all because that sort of was transitioned over into AFRL, and the network that they have is sort of deployed and operating within their research area. So these are the list of products that are space weather. And so I actually want to break up one other thing. There's a whole collection of neutral atmosphere products that are provided. Nick has done a lot of work of assimilating COSMIC-2 data, neutral atmosphere products for forcing of WACM-X, and that has a lot of value. I will not be adding any of that observations, but fundamentally, those neutral atmosphere RO observations are already sort of built into the JEDI system. There are data assimilation operators that are going in there. This whole sort of gridded data product is sitting there, integrating neutral atmosphere data assimilation into a space weather environment. I think should be maybe not perfectly free of friction, but should be doable, I would guess. So the data products that are provided, absolute TEC is sort of the primary data set. It is provided at 1 hertz, and we provide both GPS and GLONASS observations. That comes from the TGRS. Not as an operational data product, but as a research data product, we provide electron density profiles. So they come from an obel inversion system that provides measurements of vertical profile of electron density. They, I think, are similar to what a TEC measurement would be, but are sort of more research based. 557th and SWPC both use absolute TEC as their data assimilation system. Now, there's a whole question to be had about whether absolute TEC or just relative TEC is valuable, and that kind of goes to whether you need a calibrated observation or not. And that is something that really, from a JEDI point of view, from a data assimilation point of view, do you have to have an absolutely calibrated observation, or can you use something that's maybe floating around in space in observation space by tens of TEC units, and that's something that you could think about. Then there are sorts of things that are really small scale, and I'll sort of, COSMIC-2 has sort of these big, large scale features, TEC, but it also has the ability to measure very small scale from an ionosphere point of view, information, including ionospheric irregularities and density depletions. And I think that that sort of is a point where from this community, some people and the observationalists or the space weather folks may be really interested in small scale, and I'm going to say small scale ionosphere depletions. And then how does that really fit within a large scale global ionosphere model? And I think that that is an important question to consider, whether you have a nested data sets or something, and what really are you trying to get out of combining these different data sets and assimilating them all together. It's complicated, but I think if you're thinking about this now, you can do this in the right way, you might have value in putting these things together. The IVM provides in situ density, which is a measurement that would be a lot like basically electron density profiles, but at spacecraft altitude. Because it samples the equatorial ionosphere, it gives you a lot of information about ionospheric density, but in a reference frame called apex altitudes. And so that is sort of your whole question about we basically fly at 540 kilometers altitude, but depending on where you are with respect to the magnetic equator, that has a very big difference in apex altitude. And that sort of goes to the whole reference frame that you're trying to, I'll speak reference frame in what you're trying to do. It's a conversation to be had. I wish we were providing operational and plasma drifts, because I think that that would be a whole point of discussion. And from a data assimilation point of view, I think that you would all love to have that. Unfortunately, we are not producing operational plasma drifts right now. I hope that we will have research products that are available in the next few months, but that is still something that is to be developed. And I will say, the data products, that the drifts that we're trying to produce really are going to be in-track drifts. Cross-tracked and vertical drifts are probably more of a research product that we will have to follow on after that. And then the IVM also allows us to produce a plasma composition and temperature measurement, which could be valuable for data assimilation as well. Here's some just examples of data that we have. These are electron density TEC products. So going up to 100 TEC measurements. One of the value of COSMIC-2 is that it really does sample spacecraft altitude is right here. So it gets a whole bunch of topside electron ionosphere TEC, and then it samples through the F2 layer. So it is really sort of it's a topside measuring system, but it is also a measuring system that goes through the F2 layer down through the F region of the ionosphere. I think that's a unique observational data set. Just some of the field, I will bring this up. People here really don't care about how the TGRS works, but it kind of is important in some of the other things that we have. So here it would be a fictional C2 spacecraft, and it is orbiting the Earth all of the time. And it is basically, it has an antenna here on the front side and on the aft side, and it's tracking everything on the fore antenna from zenith all the way down to the local horizontal and all the way down to about 90 kilometers tangent point altitude. And we separate that out by an arc, basically a topside measurement, and an occultation, which is basically from spacecraft altitude all the way down. And there's differences as we profile through the F region of the ionosphere. We are getting small scale variations of ionospheric scintillation, and we're geolocating in and getting density depletions associated with those geolocations. So there's kind of a point there. So if you would just have a general POD antenna on a general spacecraft, you would be sampling only topside ionosphere only. It just is something when you're thinking about a future mission, or if you were thinking about observational systems, if you really want them to be a space weather observation system, you should think about your sampling and field of view. And then we basically have a similar thing on the backside. So we have a fore antenna and an aft antenna, and we are collecting a lot of observations all the time. Almost all of the data, the TEC data and the electron density profile data, is basically coming from 1 second data that's collected at 1 second observations. There's a whole bunch of data that I'll talk about for bubbles and density depletions that comes at either 50 hertz or high 100 hertz. But it's this sort of question about scales again. What scales, temporal and spatial scales, do you really want to think about? The other thing is, and this is the latency. So COSMIC-2 is providing observational data products to SWPC at about 30-minute latency. This is latency in 2023. It's not the most recent plot, but it is similar to what we have. And so it's really the only global ionospheric observation system that is making global observations and delivering it to an operational data center within 30 minutes. Now, there are other data sets that are out there that have different timescales and maybe different time steps. And so, as you were thinking about the cycling, or as you're thinking about, different observations, you have to think about what is the time resolution, where are you going to have your cycling systems going, how often they're running. I would think that you want to think about that as you're moving forward. But C2 and potentially future missions will have a strong need for low latency data. And so you will have to have a really quick cycling system on that. So here is, one of the big key things that we worked on really hard was producing absolute TEC measurements. Nick was really involved in these things. And so validating and calibrating our total electron content measurements was really a hard thing. And so we ended up doing that by comparing early in the mission, comparing our TEC measurements with measurements from Swarm B. And we did it was early in the current solar cycle. We could figure out that we are observing, we basically calibrated our Swarm B by looking at very high latitude observations, assuming that there was very little ionosphere TEC or plasma TEC there. And then we could say, okay, we have an idea about how our swarm TEC was, and then we could basically scale that swarm TEC accuracy and compare comparisons when swarm would go from the equator or from the poles into the, I'll say, the C2 equatorial region, and then we could find overlaps on that. And so here we have sort of a scatter plot when we were making these comparisons of just 3 spacecraft. Each one of these colors is a different COSMIC-2 spacecraft, and these are very low TEC values. This is total TEC, slant TEC, from 0 to 20 tech units. C2 TEC compared to swarm TEC. Through this sort of bootstrapping process, we were able to show that we were accurate to below 3 tech units, which was the requirement for the mission. That was a lot of work. And then, and it sort of goes into this point of how accurate of observations do you need, and what are the error bars that you need on any observation that you're going to assimilate. The errors and the covariance matrices, how do you want to frame that if you're going to have a new observational system? What are the requirements for that observational system? And how are you going to validate it? It is really hard to validate something in the ionosphere right now because there's nothing else for you to compare to. You can think you're making great measurements, but how do you find another? You can't go up there and take that measurement no matter what you're trying to do. So specifying these errors will be really a challenge for whatever sort of data assimilation you're going to do. We were then able to take this, our C2 GPS measurements, and compare them to GLONASS. And so GLONASS was a totally new data product. There are differences in how GLONASS signals are tracked compared to GPS signals. And this was sort of showed that when we were looking at exactly the same direction between a GPS and a Galileo or a GLONASS satellite, we were able to show the comparisons there. There's a little bit difference between Galileo I'm thinking about Galileo a lot right now because we just uploaded a new version of firmware that's tracking Galileo. But when you're comparing GLONASS to GPS, there are different altitudes of the spacecraft, and so you have to make some adjustments, and it's hard. And so calibrating these observations is not easy. But once you do that, then you can compare to other things. And so this is a little slide that I put in. So there's a whole bunch of commercial data that is coming out, and this data comes from a NOAA-funded commercial or satellite commercial space weather data pilot. And so we processed a whole bunch of data from 2 companies, Spire and Planet IQ. We were able to compare Spire data to COSMIC-2 data, and we were able to compare Planet IQ to COSMIC-2 data, and those comparisons came out quite nice. It took a lot of processing to get those 2 things together. It kind of goes back. Do you want absolute TEC or do you just want relative TEC? You have to define your measurements and how you're wanting to use these within a data assimilation system. That stuff matters. So all of the sort of large scale TEC measurements that we are providing are from a neutral atmosphere point of view are kind of synoptic, right? They're large scale things. But there's a whole bunch of stuff in the ionosphere that is really small scale and small scale in orders of magnitude. And if you're going to have a modeling system, an ionospheric modeling system, what are the spatial scales that you're trying to resolve? Now, here is a profile again from one of the first slides. And so this is the TEC profile. And this is a measurement of basically amplitude scintillation. So the variance of the amplitude measurements on the GNSS signals that we're tracking. And it's called an S4 scintillation index. For the people who are ionosphere specialists here, I apologize that if you feel like I'm talking down to you. For the people who are data assimilation people, I hope that this is helpful for you. So S4 is basically, what is the variability in the ionosphere along that track? And here is this elevated S4, and this is basically the noise on our phase measurements that we're making. And so this is kind of a signature of what ionospheric scintillation would look like. Scintillation goes back to some of the original sort of discussions earlier today. Ionospheric scintillation matters for communication, satellite communication systems. It matters for GNSS tracking. It matters for a lot. And so are you going to have an ionospheric model that has an embedded scintillation system in it? That's maybe a potential. You have to think about that. But so as we're collecting this high rate data, so as we're collecting this 1 second data, we have a little trigger that whenever we see this elevated S4, we download a whole bunch of high rate data and we do some additional processing on it. And that processing allows us to make to geolocate, to basically really identify within about 1 degree latitude and longitude where that scintillation is happening in the ionosphere. So it's a path length of approximately 6,000 kilometers that we're looking at, and we are sort of tracking down within about 1 degree latitude, longitude, about where we think that scintillation is. And so this is a map of gold. I think that there'll be a presentation on gold data assimilation tomorrow. This is a picture of what a gold image looks like in black and white. And these sort of black streak, or these dark streaks are depletions in the ionosphere here. And for the data assimilation people, these would be called plasma bubbles. There's the equatorial ionospheric anomaly, an ionospheric crest here, these sort of wider signals. This, again, for the ionosphere people here, I apologize for being so simplistic. But for the others, is that this is a part of the ionosphere that's really complex. And as the sun sets, these plasma bubbles can come up, and it matters. And each one of these little circles here is where the COSMIC-2 data has collected high rate data and geolocated and overlaid on top of these bubbles. And so the point here to say is that we are really observing these bubbles in real time, and we're tracking them, and we are creating a data product out of that. From a global TEC point, I'm not sure that you can resolve these bubbles. And so what are you going to do with this? Are you going to take these depletions? Are you going to remove? Are you going to take? Oh, sorry. Are you going to take? Oh, sorry. I'm screwed up here. Let me back up. Are you going to basically say, whenever we see this scintillation, are we just going, or how are we going to handle that data? Are we going to flag it out? Are we going to assimilate it and say that it's all the same? It's a point of complexity that you have to think about when you're merging these things together. So if you add all of these things together, we've created, and along with help from Boston College, an operational data product. And so every 15 minutes, we're computing basically a bubble map here. And so these bubble maps are using these geolocations, scintillation geolocations, using an algorithm developed by Keith Groves and Charlie Carano. And we are basically defining where we are seeing scintillation in a kind of a simplistic coordinate sense. So basically magnetic longitude, and then we're specifying the latitude extent of it based on a climatology. So it's, how are you combining these things? It's an interesting thing. And if you don't even care about scintillation, then you just ignore this and you sort of move on. But there's a component to maybe have an embedded large scale ionosphere system with an equatorial scintillation sort of model. I would guess that these things are sort of, I would guess that somebody has integrated a thing like SAMI 3 into like WAM or into like Whack-A-Mix or something, or at least somebody is thinking about that. I don't know everything about that, but this is a data product that we're delivering. We're creating a net CDF file. So that's a pretty simplistic gridded file that the Joint Center would be very familiar with assimilating or using, but then we're pushing it off to them. And so, there's a lot of variability here. It does not, you have to just decide how you're going to use these sorts of things. In sort of the same mode, well, in the opposite mode to the bubble map, we're producing basically the opposite sort of thing. And so for where are we certain that there's not any ionospheric scintillation? And this is important. And so this is an all clear measurement, and it's a UHF all clear. We'll have an L band all clear, so two different frequency domains where this is happening. And so we're basically, these green areas are where we're very confident that there's not any ionospheric scintillation going on. So if you are having a problem in your UHF transmission at some point and you are in one of your green areas, you're have a problem that's probably not related to ionospheric scintillation. And so you have to look for someplace else. That is not really a joint center sort of data assimilation product, but it is a problem, but it sort of allows, if you're thinking about what data products to put out, that would be the sort of product that might be valuable in the future. 2 minutes. Oh, good. I'm glad I took some things out then. So I'm coming back here. So then I think the next thing I'm going to put out is related to the IVM here. So almost everything I was talked about was GNSS. IVM, so this is basically the top plot is a 24 hours of satellite tracks for COSMIC-2. The middle plot is basically 1 hour of ground tracks of each of the 6 COSMIC-2 spacecraft. So we are sampling basically all longitude sectors or all magnetic local times, all local times over the equatorial ionosphere. And that allows us to basically, for the IVM, to measure in situ density measurements over time. And so as the terminator is here, as we go into the evening component, sunset, post-sunset component, we see all of these things here. Now, for the data assimilation people, you think, oh, that's just noise, I don't want to deal with it. But for all of the ionosphere people, they're like, those are plasma bubbles. We really care about that for whatever reason. And so you have to think, this is a logarithmic scale here. So 10 to the 5th units, or 10 to the 5th electrons per cubic centimeter versus 10 to the 3rd. That is a huge dynamic range in a model. How are you going to really absorb that? Are you going to absorb that? I think you just have to think about that. I'm almost done. I put these in at the last minute because there's another thing that is happening here is that, so this is not space weather, but this is basically what is our signal to noise ratio that we're observing over a global scale. This signal to noise ratio goes into things like our S4 measurements. And so this is basically, I think, only a week worth of data for us, but it is a 5 degree by 5 degree box of what our SNR is over each one of these geographic points. And you see over the South China Sea, over the Middle East, that you see these depletions. And really this is coming from RFI, coming from ground sources. And the point of that is that there's a whole bunch of things that are now happening on the ground. And if you're measuring, there's not really any quality checking or quality control that is going into ionosphere data assimilation right now. And that is a whole component of things that you probably have to think about. I worry right now that what is going on in the South China Sea and how is that impacting our scintillation? How is it impacting our data products? I don't really know how that is. I don't have a strong feeling right now what that is doing to us, but I feel like we're going to be thinking about it for the next year. And for a data assimilation person, we should probably tell you what we find. Here's a subpoint based from the neutral atmosphere. You can really see it more directly. This is an error statistic that we get for all of our neutral atmosphere products, and it is just very strung out what we're seeing around the globe. So in summary, C2 is really an equatorial ionospheric observation system. It provides real-time data over all local times and over all longitudes. It has sort of 2 different components of spatial scales, the large scale TEC and the small scale ionospheric scintillation. And maybe some groups want some of that data and some groups want the other, but I just think that it's, when you're doing a data assimilation system, you may want to think about what scales you need in your modeling system. And validation, and so as we move into the other observations, validating and specifying the accuracy of those observations is important, and you have to think about how you're going to do that in the future. I'm done.
Thanks, John.
Yes.
We'll have like an hour, hopefully, if everybody don't overtime, then we'll have an hour to talk about the observation at the end. We'll
Yeah.
give the question.
Oh, so then the next talk, sorry. So the observations one is not me, who's the next talk?
It's Fabrizio Sassi.
Fabricio. I don't know. I guess we'll have to figure out. No, there was one other one. I'm sorry.
There are actually two, so we have two talks. The next talks for Fabrizio Sassi, they're going to tell us more on the NASA's development.